All right. Okay.
Good afternoon, good morning, good evening to everybody. We are going to begin with this new talk in our seminar. Today we have Jérôme Le Rousseau from Université Sorbonne, Paris Nord, and he's going to speak about waves and domain of determinacy for a timelike curve. So thank you very much for having accepted to participate in this seminar, and you can start as you want.
Okay, well, Enrique, thank you very much for the introduction. I'd like to thank the organizers of this seminar and all of you who are now connected or who will be watching later. I know that some people will do that because they cannot attend at the moment, and I thank them also. Well, I took the liberty to change a tiny bit the title of the seminar, not my title, but the actual name of the seminar, because I thought that crisis with a singular was rather odd at the moment. So I thought we could have an additional plural there, which we'll all agree that's what we're having right now. So I want to talk indeed about, at the beginning, some very well-known stuff, which is if I know that a wave is zero somewhere, what is the extent in space and time where I know for sure that the wave vanishes, and that's what we call a domain of determinacy. But so at first it would be very classical, and maybe you won't learn much, but then we'll do some more unusual stuff, and then there might be some surprises at the end. Before that, I'm going to take the advantage of having this audience to mention this journal that is fairly recent, yet it's a journal that is the journal of the Tunisian Math Society, and it aims at publishing high-level papers in all branches of mathematics. So therefore, I encourage all of you, if you have papers of good quality that you want to have published in that journal, please do so. It's as you can see, maybe you can recognize the publishing house, which is MSP, which is a very serious house, which is non-profit. And for instance, the journal you may know from this publishing house is the journal Analysis and PDEs, which is a highly ranked journal. And we hope that this new journal, well, it's already a few years old, will be soon also highly ranked. So now I'm going to, if I manage to switch, yes, talk about the content of my talk. So here we'll have d dimension in space, and one additional dimension will be time. And to simplify things, what you can have in mind is your favorite wave operator. So dt squared minus some Laplace version of the Laplace operator you like the most. So here I put a matrix. So the symbol, if I go in the Fourier domain, is given by this small p here. Do you see my where I put the hand of
Yes,
Acrobat here?
Yes, we see.
Okay, you see that. So when all right, but we can be more general than that. We can think of R1 plus D to be a Lorentzian space, which means having a metric at every point t and x, which I will now call y. Y will be tx. And at every point y, well, you have a non-degenerate bilinear form, and it has this signature -1, which will be for what we will call time-like direction. So the vectors dt that points in the time direction will be associated with this negative sign, and all the other space directions. So we have d times +1 in the signature. So space, you have a positive number, a positive is associated with a positive eigenvalue if you want, and the only negative eigenvalue is somehow with the time direction. So then the symbol of the operator, our wave operator, becomes what is here. So we just have this metric, and it acts on eta, and eta here as tau as the first component, and then psi1 and up to psi d for the other components. So if you want, it's going back to the first operator, but you also add terms that involves both dt and dx, and they are second order, of course, at most. So this is just the principal part of the operator we have here. Of course, the most basic of all these examples is the Minkowski space, where the metric is this one, which is precisely having dt squared minus the flat Laplace operator. But of course, you can also have, like the earlier example, a Riemannian metric, which I call G here, which is not the previous one. It's just in space this time. And then you can form a natural Laplace-Beltrami operator on RG or on a manifold, but I won't consider manifolds here for simplification. And with the dt squared, it gives you this minus d tau squared. Okay, so it's a bit more general than the wave equation, but wave equation is pretty much sufficient. So if you feel more comfortable with the first one, then keep that in mind. And we shall allow t here to, the coefficients to also depend on time. Okay, when we do that, and I use this Lorentzian metric, as I said, a vector for which it gives me a negative sign, which it's called timelike. It's here on the slide. I have a timelike vector. If it gives 0, then we call that vector a null vector. And if it's positive, then we call that a space-like vector. So in blue here, I have a cone, which is at a point y, or here I put it at, it's on near a point, any point y, I have such a cone. And in blue here, I gave you the set of timelike vectors. So that's what I call gamma minus at point y. And of course, when you move, since the metric is different, then this cone will change. Here, it looks isotropic. It has no reason to be isotropic, this cone. Yet, it is convex. And what I call a timelike curve, it's a curve here indexed by the variable s that moves, that goes into my space, which L here is just R1 plus D. And all I ask is that its tangent vector here lies in that blue cone almost everywhere, because I can ask this curve to be only Lipschitz. On the other hand, I can also, and I will also consider hypersurfaces given by, usually by as a level set of a function. Here, I take the level set equal to 0. And I'll call that hypersurface space-like if I put its differential in the symbol of my wave operator, and that is negative. So if you want, I want df to be time-like. The thing is that what you have, if I go back to, I don't manage to move back. Yes. What I have here in the symbol here is in fact, I wrote it down. It's the inverse of the metric. And so when you look at vectors, you use the metric, and when you look at differential, which are covectors, you use the inverse. So that's why it's not the same cone, but still they are connected with one another. So here I ask df to be timelike if you want, but in the sense of covectors. Here, the blue cone here is the cone of timelike vectors. So doesn't have, this is not very important, but it's not the cones are reciprocal of one another. Okay, here is the type of results you can have for waves starting for space-like hypersurfaces. Later on, we'll talk about time-like curves, but at the moment, let's talk about space-like hypersurfaces. This is very old. I mean, it started with Holmgren's theorem, which is only for analytic coefficients, but then this was extended for non-analytic coefficients, in particular, if you use the work of on Kahneman estimates by people like Hermander, who used pseudo-convexity. The theorem that I mentioned, I give the name of John, but this was for analytic coefficients. It goes like this. I have I mean, t equals 0, so it's my initial time where I put my Cauchy conditions. I take an open set of that clearly space-like hypersurface, which I call omega here, and there, in a neighborhood of that omega, I should have put the closure because the neighborhood of omega doesn't mean much, but in the neighborhood of the closure of omega, I set the Cauchy data, u at time 0 and its time derivative to be both 0. It's missing, obviously, here. It should say equals 0. And I have a wave, a free wave, so I don't have any source term. The question is, where can I know for sure that u is 0? Well, the theorem goes like that. If you take an hypersurface, which is represented here by my lines here, and I deform it, and all the time there's this expression that when you deform it, but still you see those hypersurfaces, they have their feet in omega. You see what I mean? And nowhere, those hypersurfaces, even though you deform them, they never become characteristic. They are nowhere characteristic. Well, then in the region that you go through like that with F, which is this, we go between level set equals 0 to level set equal 1. Here it's represented. 0 is really omega, and 1 is this upper one here. Well, then you know that since you are not characteristic in that region, then u will be 0 in this whole region. So basically, you see that with this, in this triangle region here I drew, because here I assume constant coefficients for simplicity, I know that I will prove that in the interior of that triangle region, I know for sure that u will be 0. And what I will call a domain of determinacy of omega, which is a subset of an open subset of t equals 0, is precisely an open set where I know for sure that u vanishes if the Cauchy data are 0 in a neighborhood of omega. And what I will call the domain of determinacy is the largest of such open sets, S missing, which is basically the union of all those open sets that you can find. It's okay, so this is what we call domain of determinacy, and there is a simpler way to think about those, and you can find that in the literature from very far in, you find that in Courant and Hilbert, for instance. A characterization of the domain of determinacy is as follows. You take now, you still have omega, which is in bold here, in t equals 0. You take the the complementary of omega in t equals 0, so what is outside. And from there, you don't shoot characteristics, but you shoot time-like curves. But time-like curve, you can let them go as close as you want to being characteristic. And so basically you recover also characteristic curves. But any point that you can reach in those blue curves here, which are time-like, will give you what is not in the domain of determinacy. So we recover that the domain of determinacy is here, this triangle. So that's a nice way to connect to another definition of the domain of determinacy. If you are interested in how to prove that, the connection between the two, it's very nicely done in this paper by Joly, Métivier, and Rauch. And I guess at the beginning, it was written by, I should have mentioned that this is a joint work with Jeff Rauch. And in that paper of Joly, Métivier, and Rauch, they show that those two formulations are equivalent for very general hyperbolic systems, including the wave equation, of course. But this is very nicely done. How do they do that? In fact, they connect, they obtain a third formulation of domain of determinacies, and this goes through the definition of the first arrival time. Let's pick some point here, which I call why not, in my R1 plus D space. And what is zeta x here? Zeta x is, in fact, it's better defined here. It's the infimum of all the times where this point x is reached by a time-like curve starting from y0. So you see I have y0 here. I shoot time-like curves, and if I'm at some x is only a space position, there's no time. I know here, for instance, there is this, there is one, it can be reached there, but there could be lower values. And if you take the infimum, you will reach somehow this black curve here. And so this defines this function zeta of x for a wave that is initiated at y0. And there's a very nice characterization of this function. It is, in fact, the solution of an iconal equation, which is a Hamilton-Jacobi equation. So P here is, again, my wave symbol. Here, there should be time, t, but that's precisely where you will have zeta of x. Here, x. For the time frequency tau, I put 1. And for psi, I put minus the gradient of my function zeta. Why is that? Because, in fact, the function, the first arrival time function, curve we are looking at is precisely t minus zeta x equals 0. We shall see that. So this is in fact, here what you have is the gradient of a function defining this black curve here. And what they prove is that this is precisely the same thing, this infimum and this solution of this Hamilton-Jacobi equation. Of course, at x0, the arrival time is precisely t0. And what you can prove is that, in general, zeta is Lipschitz. And near the point, near the tip here of this black cone, if you want, it's not a cone in general, it's going to have a more complicated shape. Well, here near the tip, near y0, then it is smooth, which is makes sense. And locally, when you solve a Hamilton-Jacobi equation, you can use characteristics and or bicharacteristics here, and it's going to be smooth. So what we just did here is to see that in the future. So I defined the future of a point y0 to be all the point tx where t is larger than this function zeta, but you can also reverse time and you can look at the past of a point. And it's all the points that can be reached by those blue curves, by time-like curves. Okay, so now we can move to what interested Jeff Rush and I some time ago, is what happens when instead of looking at space-like curves, we look at the time-like curve, which is my blue curve that you can see here. And I know that there is an open set, a neighborhood of that blue curve, or at least part of that blue curve here between gamma 0 and gamma 1. Gamma is my blue curve, my time-like curve. And there's this open set, which is in blue here, where I know the solution is 0. Where is the solution 0 away from, I mean, where can I push, like I did before that with, where can I push things to know that I am 0? Well, there's a very nice theorem that was not possible at first with what was done. I mean, it was of course possible with the Holmgren theorem for analytic coefficients, but with the techniques of Kalman estimates using strong pseudo-convexity, it was not possible to prove that. And there's a sequence of papers, and the first one was by Luc Robiano, and then there was some major improvement by Daniel Tatarou, and then there were papers that kind of finished the work. And what does it tell you? It tells you that if you take a sequence, let's say, let's start from one hypersurface. If I have an hypersurface, and this hypersurface is such that its differential is space-like, which means like if you put it in the metric, here the co-metric, it's strictly positive. And it's like this everywhere. Well, then if you know that your wave is 0 on one side, you can cross locally this hypersurface. And therefore, if you take a sequence of hypersurface that you deform hypersurface, and you still keep that property that you are never characteristic and you remain, the differential remains space-like, well, then it's going to be exactly like in the John theorem. You will take being 0 in my blue open set to being 0 in a much larger open set following that deformation. So that's why I said that U is going to be 0 in f-1 of when on all the level sets of f, my function, that goes from 0. Here 0 is inside my blue open set, and f1 here is here. And you feel that you can push that as far as the characteristics, and it's precisely what is given in the later papers. If you are interested, those were just unique continuation papers, but they were not. There was no quantitative version of that until recently. There's an article by Camille Laurent and Mathieu Leoto that give a very nice quantitative version of this theorem, and it's usual in unique continuation. It's not a Lipschitz. It's not a Lipschitz continuity. Of course, it's much weaker than that. Why is that interesting? Why is that article? All those articles interesting? Is that well, in approximate controllability, usually you will know that you vanish somewhere, and you may wonder how far can I push that to know that my function is truly 0 everywhere. I'm thinking of the dual space of a controlled equation, and if you have that, then you will be able to know that you have this unique continuation globally, and therefore you have approximate controllability. The nice part of about the paper of Laurent and Leoto is to quantify the cost of the control. It is also interesting in inverse problems where precisely this approximate controllability can be used. And I refer here to the boundary control method by Belishev and Kurilev. But still, with those articles, there is no description of this domain of determinacy, of what the domain of determinacy is. How far can you push that? Okay, you have this vision. Okay, I'm going to push hypersurfaces like that, but hypersurfaces can be quite cumbersome. Before we saw that we could use timelike curves to obtain the domain of determinacy in my open set omega that was in a space-like hypersurface. So can we do similar things? Well, not exactly that, but okay, what is our intuition first? I mean, our intuition is that I can look at, if I take my point gamma 0, which is the earliest time in my timelike curve, I can look at its future. And I know all timelike curves will go there, and I won't be able to exit that if I start from by deforming. At least it's the intuition that one can have. If you deform hypersurfaces, you won't go beyond that. Well, similarly, you can look at the past of the point gamma 1, and you have the same impression. So you are interested, in fact, in the intersection of the two. And that's what Jeff and I call double cones. You intersect the past of gamma 1 and the future of gamma 0. And this looks like, when you think of it, this looks like the answer to our question. So that's what we tried to prove for quite some time, that those double cones are the answer. Those are the domains of determinacy. But since it resisted our attempts, we thought that we needed some tools, and we wanted to have something that doesn't use hypersurfaces but uses timelike curves. And so we thought of deforming timelike curves, having what we call a homotopy of timelike curves. So x here is a continuous function of a first parameter, which I call sigma. And here we have sigma 0, and here we have sigma 1. And for each sigma, we have here a C1 curve, which will be my timelike curve with parameter which I call S. Okay? So sigma is the homotopy parameter, and S is the parameter of each timelike curve. And for future reference, I'm not going to talk too much about solutions of waves. So when I have an open set in R1 plus D, what I will call Z O is my open set, it will be the domain of determinacy. I know that it exists, and it's the largest open set where U vanishes if it vanishes in O. Okay, maybe there's something missing, but it's on the drawing. What I ask for my homotopy is that it's for each curve, they have their feet here in my open set O, where I know that my solution is 0. And also their head, what I'm going to call here their head. It's not, since here it's the foot, it's going to be the head up there. For S equal 1, it's also in 0. And also the initial curve for sigma equals 0 is going to be in that blue open set. And our conclusion is that if we have this setup, then the whole curtain, if you want, it's like we seem like we're drawing a curtain when this whole homotopy, the image of the whole homotopy, is in the domain of determinacy. And in fact, with the Robiano, Tataru, Zwili, Robiano, and all those authors, with their results, we're going to prove that. And I'm going to try to do it with drawings only. Okay, well, drawings only. I'm going to introduce J here, which is the set of all sigmas in 0, 1, where the image, oh, here there's a bracket missing. The image of 0 times sigma closed times 0, 1, this is in the domain of determinacy. Well, first of all, this is non-empty because 0 is in J. Second of all, it is an interval from the very definition. Third, well, if you have such a sigma, if you have the supremum of that, the sup of J, since Z of O is open and X is continuous in the sigma variable, well, you can see right away then that the supremum has to be either 1 or it's not in the in J, which means J is an open subset of my closed interval 0, 1. So the only thing that remains to be proven at this stage is that J is closed. Since 0, 1 is connected, as everybody knows. All right, so let's do that. We take some sigma bar here, and we take a sequence in J that converges to sigma bar. And since even for sigma bar, the foot and the head of the timelike curve is in O, therefore in Z of O, we only have to prove that any point we take an S bar in 0, 1 and open, not 0, not 1, and we only have to prove that the associated image X of sigma bar S bar is in our domain of determinacy. Let's look very, very closely at this point. Very closely, our timelike curves looks like almost like a timelike line. I mean, this is not the important part, but it's just to say that I look very closely, which means nothing mathematically, but we all know what we talk about. I just don't want to write epsilon and deltas here. This is my cone of timelike vectors, which I call gamma minus. So here it's the gamma minus associated with M bar. I'm going to look at points that are near M bar. So there, the metric will be a bit different, but still my metric is sufficiently smooth. And let's assume here smooth. Therefore, I can use some cone like this one, which is kind of a safety cone. That means even if I move around, the blue cone will remain in a version of this pink cone, which will be the same version. I mean, I'm just going to translate that cone from one point to the other, that pink cone, and the blue cone will change, but there will still be space between the two. That's why I call it my safety cone. And I'm going to get closer and closer with my curves. They will look like that. And like I said, on that sigma n curve, the blue, my pink cone gives me for sure. So you're going to tell me, hey, you did it the other way. You should have gone inside. No, in fact, what I want is some safety cone for space-like vectors. And this is what I will do. And therefore, you see, next to this point, I can deform I can create an hypersurface like this, starting from very close to the timelike curve at sigma equals sigma n, and I can deform it like this, and all the time this covector here remains space-like. So I know for sure that if I was 0 with the Robiano-Tataru theorem, I think I forgot to mention that in the Robiano-Tataru theorem, there is a strong assumption, which is you ask the coefficients to be smooth with respect to x, and yet analytic with respect to time. There are still open questions around that, but that's the best we can do at the moment, okay? I forgot to mention that, but that's what I assume, of course, here. So my metric is analytic with respect to time and smooth with respect to x. So now I deform things. So I use that version of the theorem with deformation of hypersurface. I can make that explicit with function, but here it's nicer to imagine. And it's nice to imagine that indeed, because of that blue cone, I remain in space-like everywhere. So therefore, I know in that blue region now, I'm 0. But the thing is that this is uniform in the neighborhood of my target point, which is called M bar. So here is M bar, and I said this is uniform. So here, this works. When I'm going to get closer with a larger value of n, it's still going to be the same size. It's not going to shrink. And so when I get very close, I'm going to have M bar in one of those. And therefore, M bar is in the domain of determinacy. So that gives me my theorem here. So here is the theorem again. Under the regularity assumption I mentioned on the coefficients, so if I can find an homotopy like this, every point of the homotopy is going to be in the domain of determinacy. Okay, now we can play with that a little bit. I'll go fast, but if I start with what's on the left, well, then I can draw a curtain and I can fill it, and then I can go up to characteristics and get the shape that you have on the right-hand side. Okay, you can play with many examples, and I won't do it because time is flying here. Okay, there is a connection that we would like to have is if I can if I can know a point can be reached by one of those homotopy, can I reach it with a hypersurface deformation or the other way around? Well, what we can prove is that if you have a hypersurface deformation, like on the right-hand side, you will be able to construct a homotopy. On the other way, we need more at the moment is that we assume that the image of my homotopy of 0, 1 square, all the points that are reached, we assume that this is an embedded submanifold. That's much stronger than what we had at the beginning, but then we can prove in that case that indeed we can construct some hypersurface deformation. Since time has been flying, if you're okay, I'm going to skip that. And I'm going to go back to those questions about those double cones. Are the double cones the answer? And can we use our new homotopy theorem to prove it? I mean, it's much more flexible than what we had at first with those hypersurface deformations. Okay, well, that's something we were able to prove is that if we consider points, the timelike curves and the endpoints are close to each other in time. You see there's this epsilon here, which is in the time direction. Of course, okay, to do that, I have to work in a compact set where, or I have to assume that at infinity, the coefficients of my metric are bounded, but let's work on a compact set. Then I can find such an epsilon. And if I take points that are close to each other in time, that means the difference in time is less than epsilon, and there is a time-like curve that connects them. And around that time-like curve, there is, I take an open set O. Well, then the double cone that are represented here that connects the 2 points, gamma 0 and gamma 1 here, which I call y and, yeah, it should have been y0 and y1 here, not y and y prime. Anyway, the closure of that is in the intersection of all possible domain of determinacy if you change this curve O. The only thing we ask is that this curve O should be the neighborhood of some time-like curve that connects our 2 points. So that's a first result, but it's for small double cones. And to prove that, I like the proof very much because it uses that the first arrival time, this function zeta that we obtained before with Hamilton-Jacobi equation, is smooth when you are near the tip here. And you see here, I drew some black cones, which corresponds to the zero set of those functions. So S here is, I have a point gamma S, for instance, here, along my time-like curve, and I look at the travel time, the first arrival time function starting from gamma S, and I construct this T minus zeta of X there, starting from gamma S. This is smooth, and what I would like is to create a vector field that is tangent to that nice cone and points towards the tip. And actually, that's fairly easy. What I do is that I consider the differential of that function, and then I use the gradient, in fact, with respect to the metric. So it's the same thing that you do with Riemannian metric, and you can take the differential of the function, but then you use the metric to create the gradient with respect to the Riemannian structure, which is only applying the inverse of the metric to the differential, and that gives this exactly this vector field. It's a bit strange, but it's because we have this -1 and d times +1 signature that this gradient with respect to the metric, to the Lorentzian metric, is, strangely enough, is in the tangent space of that cone, not at the tip, but at the point we consider. But it's also orthogonal with respect to that cone. Of course, with respect to that Lorentzian metric. So there's no contradiction here. You should not think in terms of Euclidean or Riemannian metric. Anyway, so, and this vector is precisely null, and it totally points towards the tip. So if you integrate this vector field, you will reach the point gamma S, starting from a point in that cone. Well, we can do that at, if we do that, it's not sufficient, but what we're going to do is deform that vector field to make it point towards negative time. The further you go, you don't deform it, you see, on the cone, the future cone, the boundary of the future of gamma 0. But for gamma S larger than 0, you deform it. I think I give, it's simply, you can give this expression here, what I call W. And now, if you take this new vector field, if you integrate it, it's going to take you from any point, and you're going to reach a point in the time on the time-like curve, but the blue curve that you're going to follow is time-like. It's not a null curve. I mean, meaning that the tangent vector is not null. It is timelike. So now we can apply that to our small double cone. I start from a point here, and I construct going in the past like that, a curve, and going in the future like that. And then I can make this a bit smoother. It's not an issue. And then this is my open set O, and here what I drew is the beginning of my homotopy. You see, one of the first curve I consider, I start on this curve, and then suddenly I apply the same strategy, and I go back to my curve gamma. Then further, when I take sigma larger, I go further this way, and then at some point I turn around, and I do that, and I have a continuum like this, an homotopy of course here they are not smooth, but we can fix that, and then I get a continuous homotopy, and I will reach this point. And you see, the original one for sigma equals 0 is in O, and they all have the foot, which is always this point here, and they all have their heads in the open set O. And therefore, that tells you with the homotopy theorem that we have with Jeff Raj, that this point here in black is in the domain of determinacy. So for small double cones, we are done. Okay, so how about big double cones? Well, let's, to discuss that, I'm going to take you close to the equator, actually. If you are in the Atlantic Ocean, close to the equator, there is a region where navigators that navigators hate the most. It's called the doldrums in English. For the French-speaking people, it's called peau noire. And what happens there? What happens there is that there's no wind. There's really no wind, and you can stay stuck there for days. Plus, so basically you can lose a race, and plus the weather can be really bad. You can have really big storms there. So that's not a place you like to hang out too much, meaning that you want to go around the doldrums. Doldrums in French, for the French-speaking people, I don't know what the Spanish word is marasme, which pretty much tells you the state of mind of the sailors that end up in the doldrums. So basically, you want to go around, and that's what happens for a wave. When you have a low wave speed region, you want to go around. So we designed a model like that with Jeff to try to understand if there could be issues with our double cones when they are big. So here we'll just have 2 dimensions in space, and we choose a Lorentzian metric, which is just associated with the wave equation with time-independent coefficients. You see, it's the nicest way you can think of that, except that, okay, the metric depends on x. And to explain the metric, I'm going to say that it gives you, the Laplace operator it gives you is like this in polar coordinates. Epsilon is here, as usual, meant to be very small. And it tells you that your wave speed, like in my drawing, is epsilon if you go in the radial direction, whereas it is 1 if you go in the theta direction. For x, let's say, larger than 1/2. And epsilon is going to be seriously small. So basically, when I'm on the r=1 circle, it will take a wave 2 pi to go around. And epsilon being, I don't know, I could ask for going in the other direction, takes 1,000,000 years in the radial direction to go across. So all I'm saying is that by taking epsilon very small, the wave propagation is going to be as if we only propagate in the unit circle. And therefore, all the phenomena and the geometry will be as if we consider a wave in the unit circle. And that's what we shall do. So here is the unit circle, 2 pi, okay, I'll call it T1 here. And what did I draw here? I drew a time-like curve on my, so now we look at R times the unit circle. And I take a time-like curve there, and I have an initial time t equals 0, and I put I have this point y0. And what is the future of this point y0? Well, the future of this point is this blue, light blue, region. So let's start. It goes like this here, but of course this is periodic, so it goes like further here. And if I go to the left, it goes like this. So you see, it's not exactly what we had in mind in our previous drawings. It's a bit stranger because of that, the periodic. We work on a manifold without boundary here. Now, if I look at the point gamma t here, and this is the past of gamma t, this a bit darker region, and in the darker region here, this is the double cone, the intersection of the future of y0 and the past of gamma t. Let's go a bit further in time. Okay. Now again, for the past of gamma t, I have this unusual phenomenon, but still, here is the in the dark region here, I have my double cone. Let's now reach the point that I called L here. So what is this point L? Well, this point L is interesting. It's on my time-like curve gamma, but there is also, you see, this null curve that joins gamma 0, y0 and L. So here, this is a time-like curve. Here, this is not a time-like curve. It's a null curve, a characteristic, if you want, here. So I have a point that can be reached by, and that's really the periodic structure that gives us that. So now let's reach this point. Well, now it happens that the past of L and the future of y0, they seem to fill up the whole space. Well, that's not exactly true because those are open sets. So there's precisely this curve here that is not in it. And what will happen? So, and here, the darker part is my double cone. What happens when I go a bit beyond L now? Oh, sorry, the other way around. This happens. And you can say, so what? Well, it happens that this double cone that seemed to be fairly continuous at first, you see, I go from here, it grows, all the points, when you move gamma t, they are close to the previous double cone. Here, suddenly, there are new points that appear, and they are far from the previous version when we were at L. And if you look at it, you can say, can I deform the time-life curve gamma t to reach points in this new region that appeared? No, I cannot. And in fact, it's not difficult in that example, not looking at the 1D, or in the 1D wave propagation, it's easy, but even going back to the model, the doldrum model in 2 dimension in space, we can construct a wave that has this pink region for support. And you see that if you have this wave that has this pink region for support, the part of the timelike curve, gamma, between gamma 0 and between y0 and y1, this is the wave is 0 there in the neighborhood of that curve. And yet, as you can see there, my double cone has a part where my wave is not 0. So which was a huge surprise for Jeff and I. It took us a long time to find that, because for a long time we were trying to prove that double cones were domains of determinacy, and in fact they are not. So the intersection of the future of one point and the past of another point doesn't give you a domain of determinacy. And this is all because for a long time, we only drew pictures like this. And we had a feeling at some point, because we tried hard to prove that they were domains of determinacy, we had a feeling that there was something wrong going on. And it took us a long, long time to figure out this example. So I liked very much making all those drawings for the talk, but in some ways, those drawings can be very, very, very misleading. And it's always good to make drawings, but well, okay, we learned our lesson that sometimes drawings are not the good thing to do. So my time is up, and I like to stop here, and I thank you very much for your attention.
Okay, thank you very much. Thank you very much. Very, very, very nice talk, very clear. And now we have some time for questions. If you want to ask a question, please switch on your microphone or make a signal or write something. There is Jean-Pierre Puel. Okay. Hello, Jean-Pierre.
Salut, Jean-Pierre.
Salut. Okay. In the first theorem with Jeff, where you show that the set that you can obtain is inside the domain of
this one.
Yeah, this one. For the proof, I think that the key point was to show that the area where the solution is 0 is uniform with respect to this n.
Yes.
Okay. Well, in order to prove that, which was not clear for me, do you use the quantitative version of the unique continuation theorem, or something?
No, not at all. No. We don't use that. What we do is that we construct a family of hypersurfaces, which are level sets, and we just look at we change the value we want for the level set, and it deforms the surfaces, and it gives you at the end what you have that. And when you take a smaller value, it shrinks, and it can be as close as you want to the curve, which is indexed by sigma n. And since we know for sure that this curve is in the domain of determinacy, because we assume that it was, then we know that this all blue region I have now on the screen is and so it's really not quantitative at all. We don't need, but we need to be able to push things pretty far.
You need the uniformity of that.
Yes, well, the uniformity of that, the uniformity of that is thanks to that safety cone that I use. Because the safety cone that I use is what you have at M bar. when I'm going to be not far from M bar, this will still be a safety cone. And so basically all we ask is that when you do those deformation, will remain in a way time-like, oh, no, sorry, space-like for the differential. It remains space-like, not for the blue cones, but for the pink cone all the time. So then it's uniform because this pink cone is uniform. It's going to be a safety cone everywhere around.
Mm-hmm.
You see, the idea is to indeed not to do the construction as far if we did the construction first for sigma n, then for a larger n, then this blue region could shrink, but here the construction is based on a safety cone that is obtained starting from the target point. Therefore, it's going to be valid in a neighborhood, and that's the idea.
Okay.
Okay,
but
thanks.
It's a true important question, Jean-Pierre. You're right, and it took us some time to figure out this. I mean, we had the intuition of that, and then before we could actually write a proof took us quite some time.
Okay. Another question, comment? Okay, I have a small question. I didn't understand well what you said about the dependence of the coefficients in the last example you showed. You said that the coefficients must be independent of t.
No, they don't have to be, but I chose them. So I want to emphasize here that this is not a problem of having time-dependent coefficients. No, they don't have to be. I could create an example with time. Well, in a way, the time-independent coefficient is a particular case of a time-dependent coefficient, but no, this is not the issue. What the issue is here, or since the coefficients are time-independent, the issue is that the time-like curve is not vertical. It's not just in the time direction, if you want. Because if you were to consider that, so if you take your wave equation with time-independent coefficient and you look at a vertical path, then you can prove that, of course, the cones are going to be symmetric with respect to, and then you won't have this behavior this won't happen at all. So we can prove that indeed, if you have a vertical path, then the double cone is indeed going to be a domain of determinacy. But this is not a big issue to have this here only x. If I had put time here, I would have asked for it to be analytic with respect to time, of course.
Sorry, can I ask you something?
I think you may.
Jean-Pierre. About the figure, the gray zone that you, okay.
You mean
what you just okay, the gray zone. The gray zone is the double cone.
Yes, absolutely. This is the double cone.
Something I did not understand. When gamma t overpass L. Okay.
Then the gray zone is also the double cone.
But no, well, the part that you show here is not in the double cone.
Yes, it is. This part here is in the future of why not, and it's also in the past of
gamma t. No, it's not in the past
gamma
of
t.
gamma t.
Yes, it is. You see, let me show you Jean-Pierre. Let me show you the future of gamma. You see, the future of gamma. I'm going to follow this line here. That's the boundary of the future. and it
Okay,
goes
okay.
here.
Okay,
And
it's
it
in the
goes like
future, or why not? I
And it's in
agree.
the path of gamma t. Let me show you the path of
Right.
gamma t. The path of gamma t starts here.
Yes.
It's below my hand.
Because
So
it's okay. Okay, sorry.
And then it goes here.
Because of periodicity.
It is periodic. Yes. Sorry. I did not. Okay.
No, trust me, it is not easy to see. Look. Well, I can show you. I make those things at some point on on paper, and it didn't help very much either. You see, I drew things, and I tried. Well, I think I have the one that is here. You have, but honestly, I prefer to have it like I have it now. I try to make 3D pictures, and it's horrible to look at. So this 2D version, it's much easier. And it's, but I agree, it's really disturbing. It's disturbing to think of, we're on the unit circle, so things go around, and at some point they meet. And you have to do it yourself and then you realize that it's truly like I said. And then the construction of the non-vanishing wave that goes through here, it's not difficult. It's because we're almost in a 1D wave propagation, and so we almost have a transport equation here, but two transport equations that are connected, that are coupled. So that is not difficult.
Any other question, comment?
What is the smoothness you need, Jérôme, on the metric?
Oh, here we didn't make any effort. So we asked the metric to be smooth, C infinite with respect to X, and analytic with respect to time. No effort whatsoever.
Just
because well, in the Robiano-Tataru theorem, well, we have to use whatever regularity they have. This is the one we have to use.
But you need to solve the aconal equation.
Sure. Yes. And for the aconal equation, yes, we take also, well, we could lower the regularity, but if with smooth and analytic, then it's fine.
Merci.
No?
Okay. Well, if there is no other question, we are going to stop here. Thank you again very much for your talk. And
well, thank you.
See you next month. There will be another conference by Manolo González Burgos in May. So see you and have a very good day today.